Assalamualaikum warahmatullahi wabarakatuh. We are from International Undergraduate Program Electronics and Instrumentation Batch 21. For now, our team will explain to you about our project for system sensor. So, today we're going to make a photodiode sensor to distance sensor. Our group consists of 5 people as myself, Hafizal Ali, Yakti Muhammad Anakapati, Ridwan Ali Muhaimin, Muhammad Rosyad Irfan Hasbullah, and Rajendra Janapati Mulki. Our team made this project to get the best grades and provide new ideas for our lecturers. For that, we make projects professionally and together to get new insights and new knowledge about sensor systems which will be used for the future. Therefore, I hope you can enjoy it and get new insights about this project. If there are errors in this video, we apologize. Thank you very much and enjoy watching this video. Wassalamualaikum warahmatullahi wabarakatuh.
For the background of this project, we are concerned that there are many accidents on tunnel construction site due to the limited information on site conditions. Therefore, this system can be used to measure the dimension of the construction site by utilizing luminosity from a light source. To implement this system, it doesn't require a lot of constructors. Therefore, it will decrease fatality rate of the construction site itself. We are aware that this isn't the final system of the project, but hopefully it can spark a new invention in the future.
So now I'm going to explain the background of why we are using an LDR with a photodiode to make a distance sensor. So the basic theory for this hypothesis of an experiment is that the LDR or light-dependent resistors are used in automatic security lights and other devices to detect light levels. Now as the light intensity or the illumination rises in the LDR reading, the resistance falls. An LDR has a resistance and little current can pass through it in the dark and in low light conditions. An LDR resistance is always low in bright light, allowing more current to pass through it. Now the LDR has a component that changes with the light intensity that falls upon it. This is what we are going to utilize to read and be converted into a distance sensor. The most common type of LDR has a resistance that falls with an increase in the light intensity that falls upon the device. And the resistance of an LDR might typically have the following resistances: 5000 ohms for daylight and 2 million ohms for the dark. This is what we are going to use in calibrating the device. And now I'm going to show you how the working principle of this sensor works. The sensor uses an LDR's photodiode ability to measure light illumination or lux and utilize it to measure distance. The LDR is dependent on light intensity, meaning the lower the resistance, the brighter the light. From this principle, we can see that this will have an effect on the analog output, and it will be lower as the light approaches the sensor as the resistance decreases. Then the analog read is converted to a different value, meaning that the value of the analog read from the LDR will be converted into a reading that is much more comfortable for the distance sensor by dividing the current output with the max output, and it will calculate the total efficiency value. Now the room length, which will be measured manually to calibrate as a reference for calibrating the sensor before it can operate. Now the sensor can be calibrated by calculating the total distance measured and then subtracting or adding the error shown so that the brightness setting is shown as more or less 0. The calibration will work in the program and we will show you in the simulation. To find the constant in the calibration, we took 10 measurements and then we calculate for the standard deviation so that we can find multiple errors in various points. From there, we calculate the standard deviation. To do that, we propagate the calculations, resulting in the best results alongside the overall error to input as the calibration constant.
So here is the result of the measurement from our system. So in this table we have attempts of the measurement, and then there are the real values which we use ruler as the instrument to measure the distance, and then the measured value is using the photodiode sensor. So we find the value of mean, where we sum up all the measured value and divide it by the total attempts of the measurement, and then we got the value of 20.09. To find the standard deviation, we use the mean value we found and then put it in the equation with the result of 12.22 with an error of 0.1. And I will show you the standard deviation the standard deviation with the graph of normal distribution, and I will present to you in this screen now.
So to prepare for the prototype, we use walkwe.com to simulate the device via a simulator. So since it is a simulator, there are almost zero environmental errors or external errors that can affect the photodiode's ability to capture the light from the light source. From the conditions mentioned earlier, we can consider that the environment is ideal. Hence, we can fully incorporate the conversion result as the valid result. Uh, to break down what I said earlier, basically, since it is a simulator, no external errors such as light diffusion or the ability of the flashlight of choice to focus on the light into one point, and the accuracy of the light hitting the actual target is ideal, therefore zero, and we do not consider the error uh, to be in the measurement. Okay, so to start the simulation, allow me to explain the schematics in the simulation as shown in the screen. So first of all, we use the photodiode module sensor as mentioned before. So the photodiode sensor consists of 4 pins. It is very simple, where uh, it consists of a VCC pin, a GND pin or the ground, a D0 or a digital pin, and a A0 or an analog output pin. So as simple as it goes, VCC pin goes to the 5-volt pin of the Arduino. Next, the ground pin goes to the ground pin of the Arduino. And lastly, since we want to make use of the analog to digital converter option in the Arduino Uno, we connect the analog 0 pin or the analog output pin to the uh, pin A0 or the analog 0 pin in the Arduino. Next, since we want to have a external monitor to display the readings converted by the Arduino, we use a OLED display. Here uh, we use a 16 we use a 128 by 64 pixel OLED display by Adafruit. The wiring is fairly simple since this is a I2C device. Uh, it goes quite similarly to the photodiode module, where the VCC pin goes to the 5-volt pin in the Arduino. Then the ground pin also goes to the other ground pin in the Arduino. Then the SCL and the SDA pin. This is where the I2C communication holds, where the SCL or the serial clock goes to the A5 or analog 5 pin of the Arduino, and the SDA or the serial data pin goes to the A4 analog pin of the Arduino. Okay, to run the simulation, first, the first step we wanna do is to adjust the maximum distance of the measurement object via the program. For instance, since we want to measure a random object,
that consists of it's that the maximum distance of the object is 40 centimeters. So in the program, we simply put 40 or 40 centimeters as integer in the equation so that the ADC can convert into a range of 0 to 40 centimeters. Next, one set, we can simply just run the simulation. So allow me to run the simulation. Once the simulation has started successfully, to adjust the readings of the OLED display, we simply just need to click on the LDR module to display the slider where we can adjust the uh, illumination value or the lux value of the received of the light received by the diode. So, for instance, if the diode receives 0.1 lux or its maximum distance or the least minimum light that it can receive, it will display the farthest point of the item measured. So, like so, 0.1 lux will display 40 centimeters. Moving on, if we increase the lux value, for instance, 50 lux, the 50 lux is received by the diode and will convert into closely to 20 centimeters or half of the measured object. So since it is quite close, the OLED displays 24.91 centimeters. Moving on, if the diode receives around 12,589 lux, or if the diode receives the light amount of light close enough to the light source, the OLED will receive will read 1.30 centimeters. Lastly, if the uh, if the diode receives almost 100,000 lux or close enough to where it only gives a little bit of slack, the OLED will display the almost exact value of the distance between the light of the light source to the diode. Next, allow me to explain the program that we use in this project. So, since we use two devices, the program is quite simple to explain. Uh, so here, this is the standard declaration of libraries that we incorporate in this program. So, for example, since we use this OLED display, uh, we included a bunch of libraries to support this I2C device. Then the rest is only to set up and initialize the OLED display so it works properly. The following program is to display the bitmap earlier as an initial startup. Next, following to the setup, uh, since we want to have a backup monitor via the serial monitor, we want to begin the serial monitor by declaring the serial begin, including the baud rate of 9600. Next is the initial display of the OLED display. Next is the actual formula of the conversion between the diode to the uh, ADC converter into the actual value that we use to detect the distance of the object being measured. So first, we want to declare a value, in this case LDR val, to analog read A0. So this line basically translates to reading LDR val to read the A0 pin connected to the A0 pin of the Arduino. From there, we want to have a floating integer declared as LDR, and then the following formula converts the LDR val or the read value of the LDR of the ADC from the Arduino to the diode from the Arduino, and then dividing it by 1015 because that's the maximum amount of ADC that can handle in this simulation. But in the real world situation, the Arduino can read into 1034 units of ADC value. And then from there, we multiply it to 100 so that we want the range from 0 to 1015 to 0 to 100%. From there, we declare another floating character, which is in centimeters, cm, to convert the range of 100% into the desired maximum length of the object being measured. So in this case, uh, we set 40 as the maximum distance of the measured object. From there, centimeter is being printed by the serial monitor. To make myself clear, this formula is strictly used in the simulation, since in real world events, there are a lot of external and human errors that can affect the measurement of the sensor. So, in order to get the best out of the measurement, we have to calculate and calibrate the errors so that the readings of the ADC device would be almost one-to-one as the actual measurement. So the following explanation would be uh, the explanation of how we get uh, the uh, the calibration constant via trial and error, and getting the error, the optimum error, and the best value from multiple trial and error measurements.